To understand the concept of intrinsic self-healing, and also extrinsic self-healing, we'd better have some understanding about the fracture mechanics. This is an introduction to fracture mechanics. So, for most of the discussion, we're going to limit ourselves to linear elastic fracture mechanics. Basically, we're going to assume that the material behaves linear elastically and even up until growth of the cracks. So the geometry we're dealing with, the simplest geometry would be something like this. We have an initial crack in the material, and in the far field, this region and this region, we call it the far field. And so the average stress applied at the far fields is just sigma. And the linear elastic fracture mechanics, basically elasticity, tells us that the stress right at the tip of the crack, this point, this is the tip of the crack, will be singular. Basically, will go to infinity. At what rate? Well, if this is the direction of the crack and I extend this from here, I can define a cylindrical coordinate system based on, and I define each point with an r and a theta measured with respect to this horizontal line, that the initial crack direction, and distance from the crack tip. So basically, this point for us, we call it the crack tip. And how singular the stress are going to be, different components of the stress, sigma ij, is going to be K1, it's a constant, stress intensity factor, we call it the stress intensity factor, divided by square root of 2 pi r times a non-dimensional parameter. So here, this guy is a non-dimensional parameter, which is a function of theta. We don't want to go to the details of this. And sigma ij is different components of a stress. So, and dependence on r is outside this function f. It's inside this square root. So, for instance, and sigma ij is what? Sigma 1, 1 is, and this could be the one direction. So this direction is the one direction. This is the two direction. So sigma 2, 2 is the normal stress in this direction. Sigma 1, 1 normal stress in this direction. And sigma 1, 2 is the shear stress. And this concept of a stress singularity, if this is the first time you're seeing it and it doesn't make sense to you, you're not the first person, okay? At least I myself, the first time I saw it, I was kind of baffled. But you have to keep in mind a few things. Number one, it's a weak singularity in the sense that although the stress goes to infinity, but it goes at a rate that the energy is stored in any circle. If I take any circle around the crack tip, like something like, oops, if I take any circle around the crack tip, the energy stored in it will be finite, unless the radius of the circle goes to infinity. But for any finite circle that I take, and it's a 2D problem, so it's a cylinder. For any finite cylinder that I take, the energy stored in the cylinder will be finite. Now, the proof of that is beyond this lecture. The other thing is that the stress in no material can go to infinity. Okay, so what happens is some plastic deformations will limit this analysis. And basically, the outcome of this is that there is a region, a very small region around the crack tip, in which this stress field is not valid because the stress doesn't go to infinity. But on the regions around it, this is actually a pretty good indicator of a stress in many cases. And so this is stress intensity factor K. Now, this is K1, and where this one, what this one stands for will become clear to you very soon. Now, if you look at this, so the product of Kij times, or sigma ij's times some square root of a length will be finite. And as a matter of fact, from experiments, we know that in many materials, now there's a lot of more science that goes beyond this lecture, but the crack grows when the product of a stress and a square root of A, the crack length, reaches a critical value. Okay, when this reaches a critical value, crack grows. So if I go back to this drawing that we had here, if you apply a certain sigma, and the product of sigma times the square root of A is very low, the crack will not grow. If you keep increasing sigma, at some point, sigma times the square root A will reach a critical value and the crack will grow. Now, what that critical value is depends on two things: the material type and the geometry of the sample you're dealing with. Okay? And you know that we always want to get rid of, we always want to be able to express engineering equalities or constants in terms of material properties so that it works for all different types of geometries. The science of fracture mechanics actually allows us to do that and define this sigma times the square root of A, basically multiplied by some geometrical parameter beta, so that this sigma square root pi A times beta, if it reaches a critical value for different geometries, for a single material, but for different geometries, the crack will grow. So this beta depends on geometry. So for instance, if the geometry of the sample I am dealing with is something like this, and I have a crack here, if the geometry of the sample that I'm dealing with is something like this, I will have a I will have a different value. So, and in all of these cases, the loading is going to be, it could be something like this, or it could be something like this. So basically what we're saying is just like the previous statement, that if this product reaches a critical value, which depends on the material and material geometry, the crack will grow. Okay, so but the factor that defines geometry is taken out and is brought up to this side. So now we have a material property that, independent of geometry, can predict failure. This property, we call it fracture toughness. Okay, and in case you want to know the units of that, well, the units of that is very clear, because pi doesn't have a unit, beta doesn't have a unit. This is the unit of length. This is the unit of stress. So the unit of K1C is going to be megapascal square root of meters. So now C stands for the critical. So if I want to complete this, I have to say this C is critical. Now, what this 1 stands for is something that I still owe you, and I will explain in the next video.